All right, so it is 4:15, and we are ready to get started in today's lecture. Let me just take my drawing off here. Okay, well, you see from this schedule list that this will be the last lecture that I'm introducing new subject matters to you. And what follows after today's lecture is that lecture number 7. So lecture ID 7 will be kind of summarizing, giving you a little bit of different point of view from the material that we've been discussing in the past. So I want to kind of like have a short summary. What all these kinematics, description of rigid bodies, velocity, acceleration constraints, so on and so forth. What that means, what is like the easiest way to understand the physical interpretation, and also I'm gonna give you a few additional tips how you can prepare yourself to written exam. And then let me see. I can see that there are some comments here. Okay, so need to reorganize my screen a little bit. Okay, where is my mouse here? Okay, so that's what's going to happen next lecture, which is a lecture ID 7. So today we're still going to learn new stuff. Or kind of we don't, because what happens today is that we will take all the previous material that we have learned to deal with, and we're going to put them in a one package. And this one package will be called as equations of motion. So it's going to be a set of equations that will describe the motion. That's what we're going to do, and that's going to be a form of ordinary differential equations. So how that will happen, that's going to be the main theme of today's lecture. And kind of, everything we learn from the constraints, everything we learn from the forces, external applied forces, inertia forces, we have to put them in the same package. And that package is then called as equations of motion. And that's exactly what we're planning to do today. Okay, I see that I was a little late today. I was in upstairs and I did not follow the comments. But I see that there is a little bit of communication between the people from different places, a little bit about how is a rotational particle. So we'll see how is a rotational particle in today's lecture. With that, let's move on and let's look a little bit about what we discussed last week. Now, week before last week, we looked how the externally applied force can be expressed in terms of generalized coordinates. And last week, we did this painful thing where we converted the inertia forces to be expressed in terms of generalized coordinates. Now, then what that means? It means that, inertia description, which basically is this one here, which says mass multiplied by acceleration, but we want to say it more sophisticated way. So we want to introduce the volume integral, and we want to do the integration over the boundaries of the body, and we want to integrate the density of each particles by doing so. But basically, we want to take mass into account, and then we wanted to see how is an acceleration. Now, acceleration, which is this vector here, is described in its original form with respect to global coordinate system. So it's x and y. So this acceleration vector here consists of two components. No good. That's not doing the work for us because we actually have to use three components. And we have to use the three components because, remember this thing? Everybody needs three generalized coordinates. So three generalized coordinates per body, meaning that the force to have to be expressed by using these three generalized coordinates. So if really making a summary, what are the things that I would like you to learn? First thing I would like you to learn that the rotational particle, no, that's not existing. The rotational particle is something that is not in this planet. So it's not possible to happen in this planet. That's the one thing that I would like to learn. And then another thing that I would like you to learn is that everybody needs 3 generalized coordinates. And it's coming directly from the kinematics that we're using. So the kinematics we're using is this one. These generalized coordinates are variables in these equations. So the variables are component of vector r, this guy here, and then the rotation and the theta in the rotation matrix, which is this guy here. Those are the 3 generalized coordinates. So now we have this challenge. So we set this challenge. So we have here inertia force is expressed by using global coordinates. And really what we want to do end of the day is that we wanted to have the same inertia forces but expressed by using generalized coordinates, these guys here. Okay, so how we can make this conversion to happen, how we can make this mapping. Usually, the kind of the nice way to say that the translation from one coordinate system to another coordinate system is called mapping. So how we can make this mapping to happen from global to generalized coordinates. Well, this is something that we can make it happen by using this concept of virtual work. And in the concept of virtual work, we have this very, very important component that is a virtual displacement. Virtual displacement of vector r, this one here, can be related to virtual displacement of generalized coordinates. So these are the relations that we are looking at. R and G, this relation. How is this relation? Well, this relation can be expressed such the way. Let me try to write this with a good handwriting. Okay, so it's going to be delta R can be expressed such the way that is partial R, partial Q, delta Q. Hopefully you can see my handwriting. So this is delta, this is partial, this is partial, this is delta. And here is my relation, and this is actually matrix. And it is a matrix because this one here, R, consists of 2 components that are projection along the global X and global Y axis. So those are the 2 components. This guy here, well, that's what you know. This guy is a generalized coordinate, so it's these 3 components. So 2 equations differentiated with respect to 3 variables. That will give me the mapping matrix that has a dimensions. That's the way that they are going to be 2 rows, 3 columns. Okay, that's what we need to make this conversion, make this mapping, if you may. Okay, so let's take a look how that goes in practice. Well, it goes practice pretty much what I just explained to you. So I'm building this relation between delta R and delta Q, 2 different coordinates. And the relation is built by using this partial operation, partial R, partial Q. So it is a partial differentiation that is needed to build this matrix. And again, let me tell you the dimension of this matrix, 2 rows, 3 columns. Okay, so then you just kind of take the mathematics in your use, and you take the mathematics, and without no further thinking, you take the mathematics, you substitute your acceleration here, you're using this mapping matrix here, and then you are able to eventually express your inertia forces in terms of generalized coordinates. Now, how it look in details? In details, it looks, well, as bad as you can imagine. So it's going to be pretty much what you can see here. So you have here eventually 2 components. 2 components of inertia forces. One that is linearly related to accelerations, and that's going to be this guy here. It will be called mass matrix. And then the one that it's when you do this substitution here, the one that will be quadratically related to velocities. This guy will be called as a quadratic velocity vector. So 2 components. And what I'm really after is, of course, I'm after, this vector here, which I would like to solve when I'm building my equations of motion. So let me already explain how it goes to you. So in my equations of motion, my kind of how the equation look like will be like this. I'm going to simplify this a little bit. So this is my mass matrix. This is acceleration of generalized coordinates, and these are the externally applied forces. Now all the forces in this case are expressed by using generalized coordinates. Exactly what I would like to do, exactly what I'm after here. So now what you can do then is that you can solve this one here. Now this of course is a system with no constraints, so it's not this simple end of the day, but I'm just explaining the concept to you. Okay, so how you can do it? So you can do it in that way that you inverting mass matrix, you multiply that by external applied forces. Now you have your expression of acceleration. Now using the numerical time integration scheme, you can solve velocity from acceleration. And again, when using that another time, you can get position. And that's what I would like to do, because that tells me the configuration of your multi-body system at any given time. Now, how it goes when you're moving in forward of time, well, you basically just redo the whole thing. You're updating your mass, your external applied forces, you get an expression of acceleration, and then you are integrating the velocity, and then you're integrating one more time to get the position. That's how the game, that's your game engine. That's how the games are operating. I mean, the ones that are based on physics. Others really don't know. Okay, then there was a question about the horror movies. What's going to happen today in a horror movie wise? Well, I'm not going to answer that, but I can tell you that, in a mountain climbing, the target, of course, is to go to the top of the mountain. This is the mountain. This is, how to be able to express generalized inertia forces. And we made it. We made it last Monday. We made the top of the mountain. So we were here and we looked at the view and it was beautiful. What we're going to do today is that we're coming down from the mountain. And those of you that are doing the mountaineering, I'm not really actually in that sport, but anyways, I have learned that if you are doing the mountaineering, the most risky business is that when you're coming down. It's same here too. So today, when we're coming down, things are kind of getting to be more pleasant in certain perspective. But at the same time, it's still something that is going to be a little bit of rocky road, and we have to be very careful what to do and what not to do. Okay, so oh yeah, I see that I have a problem in my settings. So let me see what's going on here. I got the comment that the figure today is a little too small. Okay, so let me modify that. Here. Okay, it should be good now. I see that now at least the whole screen is visible. Yep, much better now. Okay, so this, when going back from the mountaineering to multi-body system dynamics, this is what we learned last week. So we learned that, okay, there's a mass multiplied by acceleration. This is really the core content when I'm solving the equations of motion. And then I have here something that we really don't know in details yet, but it will be called as a quadratic velocity vector. It's related to, well, of course it's related to mass matrix, because those two guys, mass multiplied by acceleration and quadratic velocity vector, those together will be our representation of inertia. And this, in most of the cases, particularly in the planar cases, this quadratic velocity vector is equal to zero. And it's equal to zero if the mass matrix is a diagonal representation. And remember, last week we learned that the mass matrix is having the diagonal form if body reference coordinate system is located in the center of the mass. By the way, go ahead and open the Socrates. The first question is related to this diagonal form of the mass matrix. And the diagonal form of the mass matrix you can get if the body reference coordinate system is located in the center of the mass. If any other location inside, outside of the boundaries of the body, it will have non-diagonal representation. I mean, it's going to be a full matrix. And if mass matrix is diagonal, that means that the quadratic velocity vector will be non-zero. So it actually makes sense to place your body reference coordinate system to center of the mass. But only makes sense in planar cases, because in spatial cases, three-dimensional cases, really nothing going to save you. It doesn't really help you much, because in those cases, their expressions will be complicated no matter what. So then, let's take a look. How is this mass matrix? So the mass matrix for the one body is matrix that is having 3 by 3 dimensions, meaning 3 rows, 3 columns. These 3 rows and 3 columns are, of course, associated to your generalized coordinates. So this is supposed to be y, and actually acceleration of your generalized coordinates. Okay, so mass matrix have 3 different components. One that is located here in the upper left corner is a diagonal submatrix. So it's a submatrix within the matrix that is having the dimension 2 by 2, and this is a simple expression as it is a diagonal representation such that the body mass is here in the diagonal components. Of diagonal components of this submatrix is equal to 0, and it basically means that if body is experiencing translational motion along the global x or along the global y coordinate axis, only what matters is the mass of the body. And that's how it, of course, have to be. Then the one that is located here in the lower right corner is called mass moment of inertia. Mass moment of inertia is associated to my generalized coordinate theta, which is rotation. Is meaning like how much inertia is resisting the rotational motion. And that, of course, depends where is that you're measuring the rotational motion. And the measuring here means where the body reference coordinate system is located at. Now, if it is in like a beam-like body, like this pen in the middle, well, the numerical value for this mass moment of inertia is low, whereas in this one end, it's going to be higher. So that's what it is. And you can get it from using pre-calculated tables. There's plenty of them. So you can just Google a mass moment of inertia, and you can get a lot of values for different shapes of bodies. So that's the most convenient way to do that or get that value. This guy here is the one that is non-zero only if body coordinate system is located outside of the center of the mass. Someplace else than the center of the mass, then this will have non-zero values. But if you put it in the center of the mass, then of course this is going to be 0, and it simplifies your expressions. So with that, so let's move on to Socrative. Socrative is on, actually. I can see that you make some comments about Socrative, so let me show it to you. What's going on? So I have only one student here. I think that I have a problem. Hold on, I think that I need to finish this. And I think what I need to do here is that I need to... Oh yeah, the problem is this. Okay, no, I want to use... Okay, are you now able to log in? Another room, because I was using another room, because I'm also lecturing in another class, and in that class I'm using a different room. So let me see. No, still is not correct. Okay, now I'm in a root room. Oh yeah, I see you guys are in. You came in immediately. So my question is, okay, let me read the question here. Mass matrix of a body is diagonal matrix if body reference coordinate system is located in the center of the mass, Body reference coordinate system is located out of the body, out of the center of the mass, within the boundaries of the body. Sorry that I was misreading that. Body has a beam-like shape. Then the body reference coordinate system is located outside of the body. So those are the four choices. One only is correct, but which one is correct? Remember, this is related to this quadratic velocity vector. So if the quadratic velocity vector is having a zero form, that means that the mass matrix is also having the diagonal form. But when is that case? So when that really happens? So out of the four options, one is correct. But what is correct? Let's hear that in after a few minutes. Then I see that I have 77 students today. I think that last Monday I was kind of having a recollection that there were 80 or even 90 students. So I see that a little less students today than usually, which is still okay. I mean, that 70 something students it's acceptable in my mind, because you can always watch these recordings afterwards, and that's also recommended when you're preparing yourself to read an exam. Let me just check if there's any comments, because I lost the window, my YouTube window. So hold on. Here. Oh, okay. So I can see that the game is on. So the guess is about the success rate. Okay, so let's make this game a little bit more complicated. So what if I'm gonna guess it correctly? What is that the award or prize that I will get in that case? Maybe I can I take you 1 point off if I guess that correctly? Well, not gonna do that. Not gonna do that. But my guess in today's success rate is, look at me, 55. 55 is extremely low, extremely low. But I'm thinking that because all these options are complicated, they are not easy to understand, because it makes your mind blowing when you're thinking like, okay, what is this, and how much it affects to mass matrix. I'm thinking that it's going to be as low as 55. But we will see that in a second. I see that I have now I have 80 students. Okay, so it's roughly the same number than on last Monday. So out of the 80 students, 66 already entered the answer. Rest still thinking. So it's now 13 students are still thinking. So momentarily we will go back to the soccer league. And then, I remember what I explained about this mountaineering and coming down from the big mountain. And it's somehow risky business, and somehow most often is more dangerous than going uphill. Quadratic velocity vector is a good demonstration how dangerous it can be to come down from the mountain. So it is the one component that I have just implied that it is complicated, but I have never really mentioned any details on it. Mass matrix already is a little bit difficult. But how is a quadratic velocity vector? Let's take a look at that. And then once I'm explaining that to you, then they will check the results from the in-class quizzes. I see that the 6 students are now not yet answered. So momentarily we're ready. Now, this is how the generalized inertia forces can be written. And again, I have here this mass multiplied by acceleration and this quadratic velocity vector. Let's first look at the mathematics, and no further thinking. Let's just look at the mathematics, how this quadratic velocity vector reads. So I have here mass matrix, the transformation matrix that is differentiated with respect to rotation matrix. Rotation matrix that is differentiated with respect to angle theta. Listen to me, because it's quite confusing when I'm reading your comments and when I'm explaining. So obviously I don't have enough capacity in my head to do these two things simultaneously. Sorry about that. So what I was about to say was that this one here is your rotation matrix that is differentiated with respect to angle theta. Okay, and then the vector u bar that scans all the particles within the boundaries of the body. Then I have here rotation matrix and vector u bar. Let's do the math. Let's do this multiplication and let's see how it reads. Okay, once I do the multiplication, this one multiplied by this one, this is what I'm gonna get as a result. Of course, this one goes here. And when this is identity matrix, 2 by 2 identity matrix, it simply disappears. When I'm multiplying this one by this one, this is how it reads. And now, it is not explained in details in slides, but you can take a look at the lecture notes where I'm demonstrating that this one here is equal to 0 because of the quantities of this rotation matrix. Remember, this is original rotation matrix. This is rotation matrix rotated 90 degrees. And when you do this multiplication, that's going to give you 0 as a result. So that's a scalar component that is 0. So what is left is this guy here. This guy, I'm calling this particular component such that it is volume integral over the boundaries of the body, such that there is a vector u bar inside of the volume integral. That's called M0. For the reason that have no reason, it's just called that name. It's like somebody's called Aki, somebody's called something else, so it's just a name. Okay, this is something that you can compute fairly straightforward manner, but again, if you can already see here, if your body is having like this kind of shape, the mass moment, center of the mass is here, because this form here in integral, this one here, this guy will be 0 if this body reference coordinate system is located in the center of the mass. Okay, so let's take a look how these components eventually are. So how they read. So this is when I'm building everything together, when I take all the components into account, when I'm doing the integration for the beam-like body. So this is how they read. So this is my quadratic velocity vector. And what is its physical interpretation? Well, its physical interpretation, it is forces that are introduced due to the rotation of the body for the body reference coordinate system. Now, if you're rotating your system with this such the way that your reference of the rotation is here in the middle, then translational forces, I think that I didn't say this clearly, so these are translational forces due to the rotation. Translational forces due to the rotation. Now, if your body reference coordinate system is located in the center of the mass and you're rotating your structure, how much force is this point experienced with respect to global x and y axis? No forces. So it's no forces, translational forces, because you can rotate this as much as you want, but still there's no translational forces in this direction due to the rotation. There may be translational forces due to the gravity, but not due to the rotation. How things will be different if you're measuring this rotation by using a body reference coordinate system that is located in one end of the beam-like body. Then you do experience translational forces due to the rotation along the global x and along the global y axis. And this much you experience that. So it's a force that is kind of like trying to push the beam outside from the rotation. And how much is the force? This is expressed by these two equations. That's what it is. Most of the cases, pretty much all the cases, well, let's just say all the cases we're dealing, as an example, we're always setting the body reference coordinate system to be in the center of the mass, meaning that this evil guy called quadratic velocity vector will disappear. Okay, so we are going to the game. The game is called Socrates, and I want to see how are the cases. So the cases, there is quite a bit of cases here. Correct value. And in my cases was 55. Remember that? 83. 83. Let me see. 83, 83. There's no 83 here. Or is there? I need to scroll up. No 83. Okay, so this lottery, we have no winner in this lottery. Sorry about that. So no extra point from this in-class quiz, but maybe next time. Now it's too late to vote. I don't accept your votes anymore because you already see how is the correct answer. Okay, so then now I got confused. Where the heck is my mouse? Here. Okay, let me take that off. And let's move on. So that was about the quadratic velocity vector. So quadratic velocity vector is how you feel the translational force is due to the rotation. Okay, quadratic velocity vector is 0 if now I have the same three choices than in the previous case, but in a different order. So I don't know what I should say here, but let me just read the choices here. And I'm asking quadratic velocity vector is 0. But I can tell you that this is related to diagonal form of the mass matrix. Okay, so it is equal to 0 if body has a beam-like shape, body reference coordinate system is located in the center of the mass, body reference coordinate system is located out of the center of the mass but within the boundaries of the body, body reference coordinate system is located outside of the body. Okay, and hold on. Game is on. So now I would like to see your predictions about the success rate. I remember I did not mention too much about what was the correct solution. I just saw the statistics. And maybe some of you recognize what was the correct solution last time. And this time, okay, this time the guys are saying 100%. Okay, I don't think 100%, but I think it's going to be high. Because the last time it was 83, so it's going to be, remember this, if it's going to be 100%, first of all, I'm going to smile like no limit. I think I'm not even sure if I can continue today's lecture if that's 100%. So it may be possible that you need to go, back to do something more pleasant than this, maybe. But if I'm able to continue my lecture, then it means that I will give you, all the participants will get 1 extra point because of the awesome team spirit, because of the awesome team effort. So we'll see. Okay, let me take this off to see how it's up, because I don't see my recording right now. I think it is okay. It looks okay. I'm thinking that today's success rate here will be 87. So really, really high. Really, really high. Okay, I see that I have 55 students that already entered the answer. Now, soon I will take my shortcut to the screen and I will show you how is that you're scoring. Now, that's going to be the last component, last ingredient that I'm introducing as next. Just putting everything together. And that's going to be my equations of motion. By the way, this is one of those big things in your life, because most of the years when people are learning how to build the equation of motion, first of all, they are crying. Because they're so happy. And it's okay to cry. You can cry because this is very private this year, so no one will recognize if you're crying in your home office. And they're telling that, okay, it's a little bit like life before and after. It's a life-changing experience. It's a life-changing experience. So we'll see how you feel about the equations of motion this year, but is one of the big deals. So I think I had enough marketing, I hope. Okay, so let me see the number. Okay, still seven students are thinking what is the correct answer. Maybe you guys can consider to set up the WhatsApp group or something that you can communicate in a way that I am unable to see your communication. That would be completely fine to me. Because even in classes, when I'm delivering lectures in classes, I usually encourage people to communicate. and say, okay, help your fellow students, because the communication is a one way to learn as well. Okay, maybe you already have this WhatsApp group. I have a high temptation to take a look at the results, but I'm still missing 7 students, so let me wait a little while. And while waiting, I'm going to move on to something a little different. And then something a little different will be how is that you can construct the system for multiple bodies. Because remember, we are speaking about multi-body system dynamics. And usually, well, that refers to the fact that, or refers or implying that we are dealing with the systems more than one body. So how is that you can deal with the multiple bodies? Now, I already given you an information that the equation of motion for unconstrained system, where the constraints are not accounted, can be written like this. So this is going to be my mass of entire system, acceleration of all the generalized coordinates, quadratic velocity vector of entire system, and external applied forces for entire system. Now, how you can construct these components? We learned that you can build a one or mass matrix for one body such that is 3 by 3 matrix. But what if you have 2 bodies? Then the mass matrix in the system level should have dimensions 6 by 6. So how you can do the construction, how you can build these systems together. Okay, I see that 4 students are still thinking, so soon we're ready to release the correct solution. Now, the mass matrix, if you deal with n-b number of bodies, you simply can put that together by taking your individual mass matrices, which all are, in this case, 3 by 3. You make the block diagonal form out from these mass matrices that are belong to body 1, belong to body 2, all the way to body nb. Block diagonal form means that there is this 3 by 3 matrix. Oh my god, the writing is very, very bad. Let me take this off because it looks nasty. Not good. Okay, so I have my big system matrix. Here I have my 3 by 3 block matrix that it belongs to. Of course, it's not the zero matrix, but it's the one that it belongs to body number 1. So let me put it here, mass inertia. Then here is where the second mass matrix is located at. So it's going to be like this. So this is my first body, my second body, and then I will go all the way to NB number of bodies. So this form is called as a block diagonal form. What is something good to remember from this form? Well, something good to remember is that, the system matrix, this block matrices do not overlap. They don't overlap like they do in a finite element modeling. In a finite element modeling, the different coordinates are coupled by making individual elements to overlap. We don't do that. We don't do that because the whole system matrix is associated to all the generalized coordinates. The vector of generalized coordinates will increase based on the number of bodies. Same thing when it comes to quadratic velocity vector. So this is quadratic velocity vector for the first body, for the second body, and the last body. And they have no overlapping, so they don't communicate. Let's put it this way. They have no interaction. They are not having the same coordinates. They don't do anything. That's just independent components, and that's it. Same holds for external applied forces. Independent one. Nothing to do with that. Okay. Then finally, the last component that I need is my vector of constraints. Again, no overlapping. These are just my NC number of constraints. And they are just in a one vector. They don't share the coordinates. They are just independent ones. That's how it goes. Now, what we're going to do next? Next, we're going to take a look at the results. Let's see if we're going to get the winner in the lottery. So this is called Socrative lottery. So I see that the 4 students are not yet sure what to vote. but I'm gonna close the game and I will show you the correct solution. Okay, hopefully this is visible. I think that I need to move this a little bit this direction. What was my vote? Oh yeah, I just say 80, 87. Okay, 90, 89, which is okay. This is quite good, but not as high that I was hoping to see. Okay, so let's go back to this correct solution of Socrates stuff. So I want to back up a little bit. And the first thing that I would like to explain to you is this one. Mass matrix of the body is diagonal matrix if body reference coordinate system is located in the center of the mass. That simplifies the expression of inertia. It clearly simplifies that, because then these off-diagonal components will be equal to 0. And if that is the case, then the quadratic velocity vector will be equal to 0. So basically what we need to do is that we need to find this option in second in class quiz. So let's check the second in class quiz, which is this one here. Now obviously, this is a correct solution. Why? Because then all these components that are integration over the vector u bar will be equal to 0. That's why. Okay, I cannot explain that in a way that, okay, how it look in reality. I'm only able to explain that in way of mathematics. Sorry about that. Okay, so we were here. So we were able to put together all these components. So constraints, mass, quadratic velocity vector, and external applied forces. So then what will happen next? Let me ask you this. So how you feel? Because I can see that it's almost 5 o'clock. So would you like to have some break, or you just good to go? You feel strong, so you don't need any breaks. Maybe you can send me maybe you can communicate with me via chat, live chat. No break. Straight ahead. Okay, no, we don't break. Okay, so somebody's saying that the break is okay, but it seems that in voting, the breaking is not winning option here. Full stream ahead. Full steam ahead. Okay, so let's do that then, because I think that I have enough. Okay, so we can have 2 minutes as proposed. I kind of feel that that's a good way, because I can go and fill up my glass of water as well. So, okay. So 2 minutes and then we will continue. And let me just explain what is the next thing we will do. Next thing we will do is that we will look how is that you can construct this equation of motion. And it's going to be exciting. Remember, I promised that this is so emotional time that many people are crying because of the happiness. And I'm sure you too will cry. So I think maybe I should set the Socrates and asking, like, are you crying? Yes, no, to see how many of you are crying. But many usually are crying because they are so happy. So 2 minutes and I will be back momentarily. We'll get started slowly. I know that it's not 2 minutes, but slowly I will open the last matter, which is these equations of motion. hopefully we have enough time today to practice that new skill we will learn a little bit. Now, so let's take a look. Let's back up a little bit and let's look at what was the thing we did in the very beginning when we started to express the forces um, in terms of generalized coordinates. And there's a question: what will happen after equation of motion? Yeah, there is nothing really happens, and then when we kind of reach the purpose of life, and then we just preparing ourselves to exam, and that's it. And then after exam week, which is maybe a holiday week for some of you, you just need to do the exam and nothing else. Then we will continue with the modeling of actuators. So it's no longer about the mechanics, but something a little different. Okay, so remember when we started to express the forces in terms of generalized coordinates. So we said that we want to look at how is a virtual work done by inertia forces, a virtual work done by externally applied forces. Now, this can be written in such a way that it is virtual work of generalized coordinates, because these are my variables now. So it's no longer a vector r, but vector q that I'm expressing my forces with respect. And I have here my inertia forces and my externally applied forces. Remember, the inertia forces can be actually written in such a way that it is mass multiplied by acceleration minus quadratic velocity vector, which most of the cases is equal to 0, but let's keep that guy involved with a little while. Okay, so now we're able to write the equation of motion like this. Generally speaking, this equation we just get, you cannot put that to be equal to 0. The only way you can actually set that to be equal to 0 is when there is no constraints, because the virtual work is equal to 0 only if your displacement, this time means virtual displacement, is kinematically admissible. Okay, so there's a lot to think, because what I just said is a small sentences, but includes quite a bit of material. So let's try to look this together. So I said that virtual work cannot be, in general case, set to be equal to 0, because this virtual displacement may not be kinematically admissible. So let's get started by looking first, what is this kinematically admissible, what it means. What it means is that the virtual displacement here, if it is kinematically admissible, it is a displacement that obeys constraints, meaning that if you have this crankshaft mechanism, sorry about my drawing. Oh my god, I need to take that off because it looks so bad. It's like a kid's art drawing better than I'm doing. Okay, this is my bodies, and this is my piston here. Kinematically admissible displacement would be something that the system move as a constrained system. So meaning that, if this is original configuration, when I'm introducing the virtual displacement that is introducing the motion like this will be kinematically admissible. You see that, the piston is moving from the original configuration, is moving to right. And other bodies are following according to constraints. So this is kinematically admissible. But here, look mathematically what I expressed here. I say that, virtual displacement of all the generalized coordinates, meaning that I cannot take the piston body here and I move the piston body here. No, I cannot do that, because there is a constraint that is preventing me to do that. So when the virtual displacement are expressed like here, saying that all the coordinates can move as they want, then this equation cannot be set equal to 0. So it's only equal to 0 if this virtual displacement is kinematically admissible. Here we don't care about that, because Obviously, we're just saying that all the coordinates move, and when they move, they for sure will violate against the constraint. So this equation in constraint cases, when you have constraints in your multi-body system, cannot be said to be equal to 0. So the constraints have to be accounted. So we have to force this equation. Let me take these drawings off to make this more readable. So we have to force this equation to be equal to 0, because otherwise there's no way to solve this system. How we can make it happen? Well, we have basically two alternatives to make it happen. So we can either substitute the constraint inside of this equation. So that's one way. This is the one that is referred here as a coordinate partitioning approach. We are not going to take a look at that. And then another one is that we can add the constraint to this equation of motion, and that's going to be augmented formulation. So we adding something to my original equation of motion. And again, why we do it? We do it because this equation as it is written here cannot be set to equal to 0 because we do not account the constraints. So the constraints are the missing component here. Okay, with that, let me move on to my third in-class quiz of today. So I'm asking, previous equation cannot be set as equal to 0 because why? And then the choices are: inertia forces are not accounted, external applied forces are not accounted, constraints are not accounted, no forces are accounted. So three options are related to forces, one is related to constraints. What is correct? Hold on. Oh, I lost. Here. Game is on. Game is on. Okay, now you guys are saying again 100%. Okay, hypothetically, think about if it is 100%. That would be really, really good for you because you would score 3 points from one question. Because first, guessing that correctly, then I'm sure you are able to enter your answer correctly. You must be able to do it because otherwise it's not going to be 100%. And then because I'm going to give you extra point because of this Socrates lottery. So Socrates lottery, team effort, and then the correct answer. So 3 points in total. So that would be really very unusual. Let's put it this way, because I don't think it's going to happen because usually I don't remember that ever happened to me. So okay, we'll see. Okay, yeah, but the thing is that because I'm talking a lot, as somebody's mentioned that I just mentioned what is the correct answer. I did, but the problem is that I'm talking a lot, and then this Socrates comes out of the blue sky, so you're not prepared to see a one. Now that's what makes things complicated. Okay. So please use this. Please set up this WhatsApp team so you can communicate via WhatsApp too. So that will be unofficial communication. Okay. So let me see. I have here 84 students, which is a good sign. It's a very good sign in terms of written exam. It really helps to understand the concept if you're following the lectures, because I'm sure that you understand that if not following this subject matter, there is no way, absolutely no way to learn this stuff. It's not just possible. It's not that what the human are capable to do. Okay. Now, augmented formulation is that what I'm going to explain next. But we'll take a look at the in-class quizzes momentarily. But let me get started from mathematics. Okay, I said that the mathematics are not important in this course. They're not important, but I need to use the mathematics a little bit here to tell you what are the ways that the constraints can be accounted. So I'm dealing with the minimization problem, which is very, very typical in mathematics. So I have my function here, my equation here, and I would like to find the minimum of this function such that I have to take the constraint into account. So I have my original equation and then my constraints. And I want to find the minimum of my equation such the way that I'm obeying my constraint. This is exactly what we do in multi-body dynamics. Minimizing equation will be this is minus. This was my equations. I want to solve this one. Well, not exactly this one, but I will explain it in a second. And my constraints are this one. Exactly same business. I remember, I think this is explained in, I don't know, maybe this is in a high school where they're explaining how to deal with this constraint or this optimization with constraint equation or someplace else. I really don't know the details, but we have two alternative approaches to solve this problem. The first one is an obvious, and it's called embedded technique. This is the one that I'm substituting my constraints inside of my original equation. So here is my problem here. So this is what I would like to minimize, and this is my constraint. So what I will do then is that I solve u2 from this equation, which will be u2 is equal then u1 minus 1. Let's put it in a parenthesis. And that then is substituted here. Like exactly that is made here. So this is my equation where the constraints are fulfilled. They are fulfilled because they are substituted inside. So they are automatically fulfilled. Okay, so how is that I can find a minimum of this equation? Well, okay, that's going to be a procedure based on partial differentiation. So I'm differentiating this one here, my function, with respect to only variable that I have here, which is u1. So when I do the differentiation, I will get this equation. Okay? Now when I'm solving the u1 from this equation, the u1 is equal to 1 divided by 2. So half. That's my solution. Okay? I'm sure you've seen this before. Now what about then another variable, this u2 variable? Again, same procedure, but this time I'm going to solve u1 from this equation, taking this other side of the equation. So u1 is going to be 1 plus u2, which is then substituted here. This is where you can find it. All right. So now the only variables that I have here is u2. This is my only variable. So now I'm differentiating that equation with respect to u2, and I will get this equation. And here I can take this one, the one in another side of the equation, and solve u2. And u2 is then minus 1 divided by 2. All right. So my minimum is then eventually, that was 1 divided by 2, minus 1 divided by 2. This is the space where I can find an optimum in that space. So that's the one way to go. And now I see that I will take a look at the in-class quiz. And in-class quiz, what happened? So I can see that my slides actually tilted a little bit. Yeah, now it's better. Back in the usual place. Okay. So let me take a look at the results, and then I will check if we're gonna have a winner in a lottery. 88. I did not, by the way, participate in this lottery, but let me take a look. 88. No, 88. Oh my God, we have 88. We have a winner. We have a winner. Yes, we do have a winner. Very nice. I need to write down the winner's name. Again, I'm not going to mention names because I'm sure that is against the law or something. Okay, but congratulations for the winner, and we only have one winner. You can find the winner when you scroll a little off from the live chat. Nice. So congratulations. So that's one extra point. Great. Okay. Then this guy go off. Okay, what is this the other alternative way that I can find the minimum? Now I really need to take a deep step to mathematics. In mathematical optimization, this is a true mathematical text. I just took it from the, I don't know, Wikipedia or a similar kind of place. In mathematical optimizations, and look, we are dealing with an optimization problem here, an extreme of function subjected to constraints. So this is what I'm doing here. So those are the elements that I need, can be reached when the gradients of both components are parallel at the point that fulfills the constraint. I'm sure this feels like, okay, what language is this? It's kind of English, but it is complicated language. So it means in practice that when I have gradients of these two vectors, which is my original function and my constraints, when they are in the same location and they having the gradients that are parallel, that's where I can find my constraint. And then there was a one extra condition at the point that the constraints are fulfilled, meaning that at the point where the constraints are fulfilled. So these are my two conditions. And then I'm introducing here one additional component because these gradients have a length which could be random. So I just have to use a kind of like scaling factor to make this equal. And then the scaling factor here is my lambda. That one here is called Lagrange multiplier. That is my way to solve this problem. Now, this is how this condition is expressed. Let me go a little bit further down. This is not very good. So this is where this ends. My full set of constraints is this. So when I have these gradients, when I put these together, and then I multiply 1 by lambda, that's my first set of information at the point where the constraints are fulfilled. So I take my constraints into account, and that's it. Let's try to understand this big mess, by using the same example we looked a little while ago. So in that example, this was my original function subjected to constraint. This was my constraint. Now you see that the variables that I'm dealing with are y1 and y2. Okay, so let's solve this problem by using the new technique we just learned. So let's first compute the gradients of my original component and my original function and my constraint, meaning that I'm differentiating this one here first with respect to y1. Okay, so you differentiate this one with respect to y1, it's going to give you y1. You differentiate that with respect to y2, so it's going to be y2. So that's very, very straightforward. You differentiate this with respect to y1, that's going to give you 1. You differentiate, again, the same equation with respect to y2, that's going to be minus 1. Now that's my first set of equation, and my first set of equation can be written like this. And it was mentioned at the place where the constraint is fulfilled. So then one additional information that I'm taking is my constraint equation as they are. Okay. I got an information that there is a problem in my connection. So it says that the connection is not strong enough to support my stream. Okay, let me check my phone and place it in a window. That usually helps. I will be back. Warning is still in my screen, so let's hope that it disappears soon. Other, everything else looks okay. Yeah, I know there is a problem in streaming quality. I don't know why. Yeah, there is a serious problem. Let me go and check my phone. It actually look okay. Oh yeah. Now I got the message back that now the connection is extremely good. Yeah. Yeah, this is because of my basement office. You should see the place because I'm seriously underground. So the only way that I can see a little bit of sun during the day is those tiny windows. But usually the curtains are down, so I don't see sun during the day. Okay, but I think that I was here. So I was explaining this new way to solve this optimization problem subjected to constraint. I was able to add my constraint to my original equation. I add my constraint with help of Lagrange multiplier. And now what I end up to have is three equations. So three equations. Remember in the previous case I only dealt with two equations. Now I have three equations. And this is enough. This looks okay because I have three equations and I have three variables. I have my original variables that are y1 and y2, and then one additional variable that is introduced because of the constraints, and that is the scalar component lambda, Lagrange multiplier. That's the way we're going to do this in multi-body system dynamics as well. Now, when I'm solving the first equation, it's going to give me the y1 is equal then lambda minus lambda. Then the second equation gives me y2 is lambda. Then the last equation gives me this, which gives me that the lambda is 1 divided by 2. And my final solution where the optimization can be obtained is 1 divided by 2 minus 1 divided by 2. Exactly same solution. But now I did this by adding something to my original equation. And something that I added was my constraint equation. Or to be more specific, I was dealing with the gradients of my constraints, and that's the one that I was introducing to original function with help of the Lagrange multiplier. Okay, so is this related to us? So is this any use for us? Yes, this is exactly what we need here, because remember we have this thing that we can deal with constraint system, and that is the multi-body system. This is the big explaining the whole story. So this is my gradient, and this is my lambda, this is my constraints. I'm simply going to replace f by something else. F going to be my virtual work, and because of virtual work, this component can be written like this. So it's mass multiplied by acceleration, quadratic velocity vector, externally applied forces, constraint with respect to variables. That's something that we do know. That is Jacobian matrix. Jacobian matrix we learned when we were dealing with the kinematics. And now I can write my equation as it is shown here. So I have my inertia forces, my external applied forces, and then constraints. And actually what I have here as a constraints is my Jacobian matrix tells me where these constraint forces are located in the system. And amount of forces is expressed by Lagrange multiplier. Lagrange multiplier is equal than amount of reaction forces. That's what it is. So there's a clear physical interpretation about Lagrange multipliers, and that is reaction forces due to the constraints. That's it. Okay, so remember in the whole optimization story, it said that, okay, I can add these two things together, my original equation and my constraints with help of Lagrange multipliers, and that's what I did. And it said that only there are not additional information that I need to account is that I need to look this at the place where the constraints are fulfilled. So here's my constraints. This is my equation of motion. This set of equation of motion is called differential algebraic equations, and it's already, everything we need. We could stop here. But we're going to take one step more because these differential algebraic equations are a little difficult to solve by using time integration schemes. Possible, but a little difficult. And that's why we're going to make one more step here. And the one more step is that we will convert this set of differential algebraic equations to be ordinary differential equation. And then we done. We're seriously done. Okay, so how it goes? It goes with the one trick. So this trick is out of the blue sky. I have not really explained it where it comes, but the trick that I'm doing is that I'm going to differentiate my constraint equation, which is this guy here, twice with respect to time. And this is what we did once before when we were dealing with the kinematics. And then we're going to call that constraints that are twice with respect to time as a QC. No clear physical interpretation. It's just constraint equation differentiated twice with respect to time. Why we do that? We do it because I want to convert this set of differential algebraic equations to be ordinary differential equations. And why again I want to do it? Because there is so many time integration schemes that works perfectly for ordinary differential equations. Set of differential algebraic equations are a little harder to deal with. So that's how I can write my equation of motion. Now it's okay to cry. You can cry. But not right now, because I think that really the emotional time comes when we are looking this as an example. Then it's okay to cry. So try to hold your emotions a little further. So then this is the whole story as a summary. So we started from this constant virtual work, and we forced this equation to be zero by adding constraints to our original equation. So now we can set this to be equal to 0. We end up to have this form of differential algebraic equations. We converted this differential algebraic equations to be ordinary differential equation, and that's how it reads. Let's take a look. What is that we were able to get? So this is our equation of motion. So is there anyone that we know in this set of equation of motion? Yes, actually we know all these components. This guy is a mass matrix. That's what we learned last week, that it is a mass of the system. So it's block diagonal representation of mass matrices of all the bodies in a system. What is this guy here? This is Jacobian matrix. And Jacobian matrix you get by first building your constraint equations and then differentiating these constraint equations with respect to generalized coordinates. That's your Jacobian matrix. What about this guy? Well, it's a Jacobian matrix with the transpose operation, so no surprises. So it's already somebody that we know. Then who is this guy? Acceleration of generalized coordinates. That's exactly what we want to have. This is what we want to solve. What about this one? This is the Lagrange multipliers, reaction forces to the constraints. This is external applied forces, very much familiar with. Quadratic velocity vector, well, often is equal to 0. And that's the one you can get by differentiating constraint twice with respect to time. So we know all these components. Okay, what happens next? Well, next, we're going to solve this thing by solving the unknowns. All right, so what are the unknowns then? Oh no, hold on, I need to take all this off. Okay, it's a risky business to click it here. No. Okay, anyway, so this is called my equation of motion. And what I will do with this equation of motion, I will solve my unknowns. And my vector of unknowns are these ones here. These are my generalized coordinates and reaction forces to the constraints. So Lagrange multipliers is a price you have to pay because of the constraints. In physics, in real life, those are reaction forces to the constraints. So now you can solve that equation by inverting this one here, this big matrix that is called system matrix. Then you have this form. Sorry that it's going to take a little while to write this down, and it's again awfully bad handwriting. Inverse, this is inverse. And then comes this vector, I'm not going to write it here. Now this is where you can actually have an expression of acceleration. From acceleration, you're solving velocity. And for velocity, you're solving position, and then you know the configuration of your system, and that's how the system performs. This one here, you just solve it once, so that's your reaction forces due to the constraint. But remember, amount of unknowns is your generalized coordinates, and how many generalized coordinates you need. Well, that depends how many bodies you have. So if you have one body, you need 3 generalized coordinates because every body needs 3 generalized coordinates. If you have 2, you need 6, so on and so forth. How many reaction forces? Same amount than constraint equations. So if you have system with pendulum like this, so this is a one body, so 3 generalized coordinates, there's a revolute joint. Revolute joint needs 2 constraint equations, so this is a system with the 5 unknowns. 3 generalized coordinates, 2 reaction forces to the constraints. So these reaction forces are forces like this. That's it. So velocity vector. So there is a question. Okay, there is a. Okay, what is that you're computing in practice? Okay, so I think this all becomes clear when we're looking at an example. And that's what we're going to do next. You're right. There are in-class quiz that will come next. Oh, yeah, I can see that I released that information a little bit. So there is an in-class quiz that is coming next. Would you like to see it? And now, answering this comment, which saying that this is confused. It's confused. It's difficult, but it all becomes clear when we're looking at the next example. So, hold on. Prior to that, in augmented formulation, the one we just looked at, unknowns are acceleration of generalized coordinates, Lagrange multipliers, generalized forces, and the final option is acceleration of generalized coordinates and Lagrange multipliers. What is correct? Oh, hold on. I need to put my Socrative on. That is on. And now what follows after that is that I try to summarize the whole story. by introducing you an example. I see that I kind of running out of the time today. Hold on. Yeah, this is difficult because we haven't really practiced it. So we look at the kind of the way we end up to this position was through the theory. So it's all about the theory. Next, we're going to look at what this means in practice. So what it means in practice is that we're going to solve this kind of mechanism. We're going to create the equation of motion for this kind of mechanism, which is a system with one moving body, primitive joint here, primitive joint here. And we basically need to follow the few steps. And that is the beauty of the multi-body dynamics. So if you deal with this system or any system you want, you're following these steps and you will get the equation of motion very straightforward and automated way. So, but I would like to see. Let me see if I can first take a look at the in-class quiz, and then I will move on to this example because I would like to explain the entire example without any stops or any breaks. I'm still missing like 40 students, so it's quite a bit of students that are not sure what the answer here. Okay, let's do it. Let's do this such the way that I will. Yeah, I think I kind of realize what I'm doing to you guys. I'm not giving you much of a time to answer these questions. I'm explaining quite a bit, and then when there's in-class quiz, I really fast show the question, and then we move on. And then we're moving on to another topic already. So let me just look at this example, and let me then go back to this in-class quiz. So how is that we can create the equation of motion for this kind of simple system that consists of one beam-like moving body? So it's just the one body. Okay. So we're going to follow the certain steps. First, we're going to build the mass matrix. Now, the mass matrix, we could simply take a pre-calculated tables and that's it. Or we can use some sophisticated mathematics and compute it. The mass matrix, I think the clear recommendation is to look at the pre-calculated tables. So the mass matrix consists of three components. The first one that is located in the upper left corner is my diagonal 2 by 2 submatrix that includes the mass of the body as in diagonal terms. Then in the lower right corner is my mass moment of inertia. And then this guy, which is the one that couples the translation and rotation, will be equal to 0 because, look, body reference coordinate system is located in the center of the mass. So this one will be equal to 0. And finally, my solution look like this. This is a mass matrix of my system. This is a mass of the body, and this is mass moment of inertia. Okay? So we're done with the step number 1. Step number 2, constrain the Jacobian matrix. In Jacobian matrix, the components that I need is first constraint equation, that need to be differentiated with respect to generalized coordinates. All right? How many constraint equations I will have in the system? I have here primitive joint, so that's 2 in total. How many generalized coordinates? Well, one moving body, every body needs 3 generalized coordinates. 3. So the Jacobian matrix will have 2 rows, 3 columns. That's how it end up to be. Okay. Let's first constrain the point P. Point P is the one that is located here. So let's constrain that. So let's first express where the point P is with respect to global coordinate system using the equation we're very, very much familiar with, this equation. Okay. Now, in this equation, the only difficult thing is that we have to substitute the value for vector u bar. Others remains to be variables. So look at this. So I need to make this a bit bigger. So the global x, the body coordinate system x-axis is pointing this direction. And we wanted to travel here. So obviously we have to travel minus L divided by 2. And this direction is going to be 0. Okay. U bar x is L divided by 2. U bar y is equal to 0. And now I'm going to constrain this motion such the way that this point here cannot move along the global x-axis, meaning that this guy have to be equal to 0. So that's going to give me the first constraint equation. So this multiplied by this, and this, and that's my first constraint equation. Second, I'm going to go ahead and redo the whole story, but this time for this point. Okay, I need to take a look at if there's any comments from your end. Okay. Where is it? Here. Okay, now this point here, I guess that you still are in a lottery, so you're still guessing how is success rate. It's okay. Okay, but we're going to look at this point here. First, we're going to express this point using the equation, this equation that we always have to do. No other choices are allowed. So if you use any other means of kinematics, it's going to be a criminal action. Criminal action. Not allowed to do it. So you always have to follow this because that's what we agreed in the very beginning of the course. Okay, so this is my equation that my vector u bar this time is L divided by 2. U bar y is equal to 0. And I'm constraining the y motion this time because it cannot move this direction. Okay, so it will give me two constraint equations, which are not visible anymore, of course, because I made a stupid mistake. And then I'm differentiating these constraint equations with respect to my variables. And my variables this time are my generalized coordinates, which are rx, ry, and angle theta. So that's my Jacobian matrix. Then the external applied forces. I only have here one external applied force, which is a gravity force, which of course applying in the center of the mass here. So this is my force vector, and it's applying origin of my body reference coordinate system. That can be expressed like this. This one here is equal to 0 because we are in origin of the body reference coordinate system. So my mapping matrix that converts the expression from global to generalized coordinates is very simple mapping matrix like this one here. So when I need to make this a bit bigger. So when I do this mathematical operation, mapping matrix multiplied by force is in global coordinate system. That's how my vector of external applied forces, generalized external applied forces look like. Okay, that's, by the way, that was step number 3. Step number 4 is a quadratic velocity vector, which will be equal to 0 because the mass matrix is having the diagonal form. My almost last step is a step number 5. QC, the one that is based on constraint equation differentiated twice with respect to time. All of the components will be equal to 0 except this monster guy that we met already when we look at the kinematics. So I have here Jacobian matrix multiplied by velocity. That's going to give me the vector of 2 components that will be then differentiated with respect to generalized coordinates, and that solution, and then finally multiplied by velocity of generalized coordinates. So it's going to be giving me this vector. And then How is my final solution? This is my final form of equation of motion. Look at this, my system matrix. So I have here my mass, my Jacobian matrix. My Jacobian matrix has a transpose operation. This is just to match the dimension, so it's a zero matrix. Here's my external applied forces. Quadratic velocity vector is equal to 0. And this is my QC vector, which is the one you get by differentiating constraints twice with respect to time. I know that I spent an hour and a half. Now it's time to take a look at the in-class quiz. And see if we have winners in this lottery. Okay. Okay, so without further ado, let's just take a look. So let me see how is the lottery. So we have a lot of votes in the lotteries. I see that, which is very good. Okay, so the correct solution or the lottery solution is this one. Oh, 82. That, by the way, very, very high. 82 is high. It's really good. You know, the one thing that makes no sense is generalized forces. Others are components that are there, but you know, I'm looking at the entire solution, which is this one here. So the unknowns are acceleration of generalized coordinates and Lagrange multipliers. We gotta practice this quite a bit more next week, but we are there. So we finally made this trip. So we started from the kinematics. We started here. We look all kind of things. We look at the constraints and everything. We look at the forces, and we were able to express the equation of motion. We made it. Now, let me take a look. If we have winner in this lottery, again, this is the solution. So it's what? I think the number was different just a few seconds back. Was it not? I think it was. 80. You see that we have a winner, so there's actually one winner. I need to write down the winners, and the winners are 82, 81, 80. Yeah, somebody clicked that C option, so I think that I'm gonna call as 82. 81 is okay as well. So, yep. So we have one winner. And then let me see if I have more winners. Oh, we do. At least two winners. We may see if even more than that. '83. There's an 83. Should we say that it's okay to vote 83 as well? We do. So we have three winners. Nice. Very nice. But you know what would be my dream? My dream would be to score 100%. And you would guess 100%. That would be really outstanding. If I would make a recording like that, I could place that to my CV. I could send that to my mom and say, oh, look, you know, here I am, 100% success rate. But we'll see if that's never going to happen. So with that, I think that I will call for a day. No, there are three winners. I was able to count that there are three winners. So, yep, three winners. So with that, let's call for the day and let's move on to team session. So see you in a bit in Teams.